Hey guys, Dr. Thomas. We are starting chapter 10. It is our last chapter of 1211. It's actually the first of 3 chapters that cover physical states in our textbook. Chapter 10 is all about gases. When we start 1212, chapter 11 is all about liquids. Chapter 12 is all about solids. And then actually chapter 13, we go back to solutions again. So the next few chapters are all talking about physical states. Why do some samples exist in one physical state versus another? That's a topic that you'll go deeper into when you get to 1212. For now, we're just going to stick with gases. When we do calculations and measurements with gases, there are essentially 4 variables that are important that we want to talk about. Pressure, volume, N stands for moles, and temperature. Let's talk units for a minute. In this chapter, units are more important than any chapter we've done before. So every time you work a problem, you got to be thinking about what units are given and what units do I need for the calculation. Okay. For temperature, we talked about 3 temperature scales this semester. In the very beginning, we mentioned that our most commonly used temperature scale in our everyday life is Fahrenheit. That's fine if we're talking about the weather and things like that. But in science, especially in chemistry and physics, Fahrenheit pretty much never is used. It's just not an acceptable scale. There are some cases where Celsius, which is used in the rest of the world, is the primary temperature scale that's used in everyday life. There are cases where we use Celsius. When we did thermodynamics, we talked about that when we do a Q equals MC delta T problem, the delta T, as long as both temperatures, initial and final, are in Celsius, the delta T will still come out right, and that's okay. But when we get to gases, that's no longer good enough. The only unit that can be used for gases is Kelvin. Okay, it's absolute temperature scale. Basically, the Kelvin temperature is directly proportional to the kinetic energy of the particles. If I want to raise the kinetic energy by a factor of 2, that means the temperature in Kelvin is going to double. Okay? It's the only temperature scale where that is true, where the Kelvin temperature is directly proportional to the kinetic energy of the molecules. So we need to use Kelvin every time we do a calculation. The moles, N stands for moles. When we have a container of a gas, it may be a balloon, it may be the air in a room or a box or whatever, any container, there's a certain amount of gas inside. If we give you the grams of a gas, then the first thing you have to do is convert that into moles. Okay, so for pretty much all of our calculations, we need moles for our amount of sample. Next unit, volume. Our preferred unit when we do calculations, especially if we're involving any constants and other things, liters is our best unit. There will be problems, kind of like I said with temperature, when we did a delta T or something, we said it might be, in previous chapters, it was okay to use Celsius instead of Kelvin. Same thing with volume here. If there are 2 volumes, we have like an initial volume and a final volume, and we're trying to figure out how much it changes, that'll be a case where we can use other units, milliliters or any other volume unit that we want, as long as the 2 volumes match. But if we're doing a calculation that just involves 1 volume for a gas, especially if we're doing the ideal gas law, in that case, liters are the unit that we have to use. So that's like the safest thing. If you're not sure, put it in liters. Okay. And then finally, our toughest one, pressure. The units we use are there are a bunch of different ones. It kind of depends on what you're doing with pressure. Depending on what your job is. If you are a engineers like to measure pressure in PSI, which is pounds per square inch. That's just a very usable unit for them that they like to do. If you're a meteorologist and you're talking about the weather, they read the air pressure with a barometer, and what a barometer is, basically they take a pool of mercury, liquid mercury, they put an inverted tube in it where the air on the outside pushes down on the surface of the mercury, it pushes the mercury up the tube. They measure how tall the column is, and then that's the value that they report for the pressure. So sometimes you might hear a meteorologist say the barometer is falling or the barometer is rising. That's referring to the height of the column in the barometer. The unit that's used, they typically measure the height of the column in millimeters. So the millimeters of mercury, if we have normal atmospheric pressure at sea level, the barometer will read 760 millimeters is the height of the column of mercury. So 760 millimeters of mercury. Sometimes I'll leave out the of and just say millimeters of mercury. That is normal air pressure, and we actually have one more unit that we use, atmospheres. If we have normal atmospheric pressure, we call that 1 ATM. Okay? And then finally, millimeters of mercury, at some point there's an Italian scientist named Torricelli, and they named millimeters of mercury, they renamed that unit to be called torrs. So 760 torrs equals 1 atmosphere. Now, I mentioned a lot of other units. There's PSI, there are bars, there are pascals and kilopascals. If you have to do a problem that involves any of those other units, you're going to have to look up the conversion factors that you need to change bars to atmospheres or kilopascals to PSI or any of those kind of things. You look those up if you need to. You definitely don't need to memorize those. The only one that you are expected to memorize for future classes is this one right here. 760 millimeters of mercury or 760 torrs equals 1 atmosphere. When we use calculations like the Idaho gas law, the preferred unit for pressure is going to be atmospheres. Okay, so those are our units that we need to use. Now let's start going through a little bit more detail about what we need to be able to accomplish. So, first of all, let's talk about what pressure is. Pressure is basically air molecules are flying around. Every once in a while, the molecules will crash into a surface. When the molecules crash into a surface, they apply a certain force to that surface. If you take the force that's being applied from the collision and divide it by the area of the surface that's being struck, force over area, that's what pressure is. Okay, so again, there's many different units that can be used, but the normal pressure exerted by the atmosphere as it hits the wall, as it hits our skin, any surface at all, is going to be 1 atmosphere of pressure. Okay. Now, funny thing, atmospheric pressure is not a constant. If you have a storm coming in, the pressure changes. A low pressure front is associated with a storm. If you have a hurricane, that's going to be an extreme low pressure front, where basically the rotation of the air around the hurricane, if you ever look at the maps, you can always see that the hurricanes are rotating. The rotation of the hurricane creates centrifugal force that pulls all the air out. If you pull all the air out, that's going to create a low pressure center in the center of the storm. So basically atmospheric pressure is always changing, but our 1 atmosphere that we refer to as our standard pressure, that is if you're at sea level and there's no storms or anything going on, 1 atmosphere is the average pressure that would be exerted at that point. Okay, so when we have these values, the first few sections of the book in chapter 10 talk about these values, and then it goes through a bunch of experiments where there are scientists in like the 1800s that studied these measurements, and they established relationships between them. Okay, so Robert Boyle just studied the relationship between pressure and volume, found that if you have a closed container and if you take a gas and increase the volume of the container, then the molecules are more spread out, there are going to be fewer collisions going on, so the pressure actually decreases. If you shrink the container down smaller, so you take a sample of gas and put it into a smaller container, then now there's going to be more collisions going on because everything's closer together, that's going to raise the pressure. So Boyle established that pressure and volume are inversely proportional. When one goes up, the other one goes down. Okay? Charles' law, he studied the relationship between volume and temperature. With volume and temperature, he found that if you heat a gas up, like say in a hot air balloon, if I heat up the gas in a balloon, what happens? Well, initially when you heat the gas up, the molecules start moving faster. They hit the walls of the balloon harder, and since in a balloon if the pressure inside the balloon is greater than the pressure outside of the balloon, what happens is, since the surface of the balloon is elastic material, the pressure on the inside pushes out, the balloon gets bigger until the pressure on the inside is reduced to where it equals the pressure on the outside. So the net effect here is, by raising the temperature, the balloon gets bigger to relieve that increased pressure that forms inside, but the increase in the temperature results in an increase in the volume. Therefore, volume and temperature are directly related, meaning if you increase the temperature, the volume will increase by the same factor. If I double the temperature in Kelvin of a gaseous sample in an elastic container, then the volume of the container will expand to be twice as much as it was before. Okay, so they're going to change by the same factor in the same direction. That's a direct relationship. So you kind of have to know which of these values are directly related and which ones are inversely related. But those relationships, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, there's a bunch of them. You don't really need to memorize all of them individually. We're actually going to kind of combine them into, we're going to have two main equations that we need to know. The first of them is, if I take the pressure, the volume, the moles, and the temperature, and if I set them up in an equation like this, PV over NT. So let's just say I have a balloon. So I'll draw a balloon on the board. Okay, my balloon is full of helium gas. If I measure the pressure in the balloon, if I measure the volume of the balloon, if I measure the moles of the gas in the balloon, and I measure the temperature of the balloon, plug all those values into this equation, PV over NT, it doesn't matter what gas is in the balloon, it doesn't matter what the temperature is, it doesn't matter what the pressure is, it doesn't matter what the volume of the balloon is, it doesn't matter what kind of balloon it is, whether it's a rubber balloon or a mylar balloon or whatever. It will always, if I plug in the pressure in atmospheres, the volume in liters, the moles in moles, and the temperature in Kelvin, if I plug all those in, I will always get the same value. 0.08206 liters atmospheres per mole Kelvin. This number is called the universal gas constant. Okay, 0.08206. Sometimes you'll see it written 0.0821. Sometimes you'll see it written 0.082. It's all the same. It's just a difference in sig figs and where you want to round it. Okay, but this value, which we typically call R, the universal gas constant, no matter what gas we look at, if we do all the air in the room that I'm in right now, if I measure the pressure of the air in the room, the volume of the room, the moles of gas in the room, and the temperature, if I plug them in, it's going to equal 0.08206. If I have my balloon I was talking about, plug them all in, it's going to equal 0.08206. Any sample of gas, no matter what it is, will always equal that number. So that's going to set up for us one of the most famous equations that you ever see in chemistry. A lot of times it's one of the few things from high school chemistry that students remember when they come to college. It's going to be the ideal gas law. Okay? PV over NT equals R. That's not how we usually write it. Normally the N and the T get shifted over. So I'm going to rewrite my ideal gas law, PV equals nRT. That is a fundamental equation that we need to know. With that equation, I can solve almost any problem that's in chapter 10. Now, we're going to take that equation and manipulate it into different forms that really with that form and one more form, we can work almost all the problems we need to. But from this equation, we can derive Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. All those other ones can come from this equation. So this is like the foundation for all the chapter. Okay, so now what I'd like to do is take a minute. I'm going to go to the chapter 10 ideal gas law worksheet. It's in D2L and it's on the shared class files. And I'm going to do number 1 off that sheet. The question states, how many moles of gas does it take to occupy 120 liters at a pressure of 2.3 atmospheres and a temperature of 340 Kelvin? Okay, so basically it gave me a pressure value, it gave me a volume for the container that the gas is going to be in, it gave me the temperature in Kelvin, and then R is a constant that I just gave you, 0.0821. Okay, so if I know all those values, the only one that I don't know is N. That's the one that the question asked me to solve for. So I'm going to go ahead and set it up. The pressure that was given was 2.3 atmospheres. The volume was 120 liters. My unknown is N, so I'm going to leave that one. R is a constant that you need to know. That's 0.0821 liters atmospheres per mole Kelvin. And then temperature is 340 Kelvin. So at this point, I should check my units. If you ever forget your units on the formula sheet that we provide with tests, the value of R is on there, 0.0821 liters atmospheres per mole of Kelvin. Basically, if I set it up right, all my units should cancel out. Kelvin cancels Kelvin, atmospheres cancels atmospheres, liters cancels liters. The only one that's left is moles, so that's what N is going to be. All I have to do is just divide these two numbers over. So N is going to equal 2.3 times 120 over 0.0821 times 340. And then the units there are going to be moles. Okay. I don't actually have the answer here, but I think that's a pretty straightforward calculation. Hopefully you can finish that up yourself. Okay, so that's an application of ideal gas law. It's a good place to cut off. Pick up our next video in a second.